My goal in this video is to provide a review of basic integration techniques, sort of to catch you up on anything you might have forgotten about integration from what we learned in our past Introduction to Calculus unit that we had last year. As always, we'll go ahead and get started with a deep breath. And let's begin. So I'm going to be covering a lot in this lesson because I'm reviewing, a lot of what we learned about integration. So first, we're going to go through a list of the simple functions that we know how to integrate at this point. We're going to talk about a guiding principle that we only know how to integrate basic functions. Then we're going to talk about some basic rules that we have for integrating combinations of functions. So the sum and difference rule, the constant multiple rule. And then the rest of the video, probably the second half of the video, is going to sort of be techniques that we can use for integrating functions that look more complicated. As we get deeper into this course, we're going to learn all kinds of advanced integration techniques. What we're really going to be focusing on today is the use of the basic rules and algebraic manipulations. So the first thing we need to do in this lesson is we need to recall what simple functions we already know how to integrate. And as far as I can tell, there are effectively 5 of them. I'm going to start with the ones that are over here on the right because in a lot of ways they're actually simpler. We memorized last year that the antiderivative of sine is negative cosine, that the antiderivative of cosine is positive sine, that the antiderivative of 1 over x is the natural log of the absolute value of x, and finally that the antiderivative of e to the x is e to the x. You'll also remember that all of these have a plus c on them because what the antiderivative is doing is it's telling you what function you would have to take the derivative of to get this function back. And we remember that the derivative of any constant is always 0. So the derivative of e to the x plus 5 would be e to the x. The derivative of e to the x plus 17 would be e to the x. E to the x minus 5,000 would be e to the x. So this plus c is really just reminding us that there's a whole family of functions that all have this thing, which is called the integrand, that would have this integrand as its derivative. Students will sometimes ask, particularly with respect to this rule here, do we need to put the absolute values? I would say yes. Will you lose a point if you don't put it there? I don't know. It depends on the grader. It depends how IB decides to write out the mark scheme. And so I would err on the side of caution. I would try hard to remember that anytime you take the antiderivative of 1 over x, it should be the natural log of the absolute value of x. There's a good reason for it. If you want to know, you can ask me about it separately. It's sort of outside of the scope of this video. Now, I left all this space over here for us to talk about this other rule. This other rule is called the power rule. Right? And what it effectively says is it says if you want to take the antiderivative of x raised to a power, what you do is you increase that power by 1, and then you multiply by the reciprocal of that new power. And this rule holds for all values of n except that n can't be negative 1. When n is negative 1, think about that. If n was negative 1, it would mean that this function would be x to the negative 1. It would be 1 over x, which basically means that's this case right here. That's that special rule right there. But for any other power of x, this is the rule that we use. So as a very simple example of this, if I asked you for the antiderivative of x to the 5th power dx, we would increase the power of x by 1, and then multiply by the reciprocal of that new power, and then remember the c. Okay. If I asked you for the antiderivative of the square root of x dx, you would hopefully recognize that that means x to the 1/2 power, and then you'd use the power rule. You would increase that power by 1, and when I say increase the power by 1, I literally just mean add 1 to the power, and then you would multiply by the reciprocal of that new power, and then plus c. Okay? This even applies for things like the antiderivative of 1 over x to the 4th dx. Our first step here needs to be that we do the antiderivative of x to the negative 4th. We rewrite this expression, and then from there we increase the power by 1. Remember that in the negatives, increasing is actually going to make the number part smaller, and then we multiply by the reciprocal of that, and we put plus c. These are all examples of how we use the power rule to take the antiderivative or the integral of a function. And this is it. These are the only 5 basic functions that we know how to take integrals of. Most everything else we are going to find out how to do the integral of by referring back to these 5 basic rules. We may pick up a few more things along the way, but they're all going to tie back to these somehow. Now, that point that I just made is really, really important. So important that in fact, that I wanted to call it one of our guiding principles, okay? Our guiding principle with integration is that we literally only know how to integrate those basic functions. Anything beyond that requires special consideration. It requires a special rule. It requires a special technique. Okay? So, and I want you to specifically take note. All right? The product rule, the quotient rule, the chain rule, those things do not exist for integrals. We can use the product rule to do derivatives of products. We can use the quotient rule to take the derivative of quotients. We can use the chain rule to take the derivative of composed functions. But when we're asked to do the antiderivative of those things, we can't do it, right? And so, I'd like to sort of take a moment here to do all of these problems wrong. And I'm going to write wrong in the video. I'm going to do this whole slide in red because I want you to know this is all incorrect, okay? So this function right here, you might be inclined to think, oh, I know what the antiderivative of x squared is. I know what the antiderivative of sine x is. Just because you know the antiderivatives of the individual parts doesn't mean you know how to deal with a product. You cannot say that this is, well, the x squared part would be 1/3 x cubed, and the sine x part would be negative cosine x plus c. You cannot say that this is negative 1/3 x cubed cosine x plus c. This is completely wrong. And if you want to be convinced of why that's wrong, I'm only going to do this for this one. A way that I could convince you that this is wrong is if this was the derivative. It's not. If this was the antiderivative, which it's not, I should be able to take its derivative and get back to the original function. But if I was going to take the derivative of this, I would need to do the product rule, right? I would need to do the derivative of the first thing. That would be x squared, and I would leave the cosine x alone. And then plus, I would leave the negative 1/3 x cubed alone and do the derivative of the cosine, which is negative sine x. And then the derivative of the c is 0. I got x squared cosine x plus 1/3 x cubed sine x. Notice that this thing I got at the end is not this. So I'm sorry that I've spent so much time doing this problem wrong, but it happens a lot. Students will try and take the derivatives of just individual parts, and we can't do that. Okay, so I'm going to do this next one wrong as well. All right, this one right here, we do not currently know how to take the integral of. I mean, it's a complicated thing. We'll learn it eventually, but we don't know yet. You cannot just say, well, the integral of the top is e to the x, the integral of the bottom is 2x squared, and yay, I remember the plus c. That's incorrect. We do not know how to do this integral right now. Same thing over here. You can't say that the integral of cosine is sine and the integral of x squared is 1/3 x cubed plus c. We do not know how to do this integral. So again, I kind of apologize that I spent 3 minutes doing problems wrong, but it's so important that you guys know you can't just take the integral of something by knowing some of the individual pieces. You have to know how the whole thing goes together. And we're not ever going to have nice, simple rules like the product rule, quotient rule, and chain rule. We're going to learn techniques that will allow us to get through these problems. So with that said, let's learn about some of the rules that we do know. Let's talk about problems that we do know how to integrate, right? Okay, so first we have what's called the sum or difference rule. Okay, if I expressed it mathematically, what I effectively say is I say the integral of f plus or minus g dx can be rewritten, can be re-expressed as the antiderivative of f plus or minus the antiderivative of g. In English, it basically says if you have an integrand that is built up of multiple terms and each of them is separated, if your integrand has several terms separated by addition or subtraction, you can split that integral into multiple smaller integrals. Okay, so for this particular problem, I might take this and say, I know how to do this piece, and this piece, and this piece, and these are all separated by addition and subtraction, so I can rewrite this as the antiderivative of x to the 5th dx minus the integral of sine x dx plus the integral of the square root of x dx. And each of these is something that we can do. The integral of x to the 5th, we increase the power by 1 and make it x to the 6th, and then multiply by the reciprocal. We know that the antiderivative of sine is negative cosine. And this last one, we might actually need to take a moment to rewrite that one. So I'm not going to get rid of the integral symbol yet, because I want to take a moment to rewrite this as this. I want to point out to you that when you show your work like this, until we are expert at this, I want you guys to show the work on this. Please take the extra 10 seconds to get a massive increase in accuracy. I'm going to rewrite this integral. Even though I finished these ones, I rewrite this integral. And now I remember I increase this power by 1. So that power is going to go up to x to the 3/2 power. I multiply by the reciprocal 2/3. I remember my plus c, and then I just fill in the stuff that went before it. 1/6 x to the 6th plus cosine x plus that. If I wanted to check my answer here, I could take the derivative and show you that I get back my original integrand. So this is the sum and difference rule. This is one rule that we have that allows us to take larger, more complicated integrals and break them down into smaller pieces. Next, we have what's called the constant multiple rule. Okay, expressed mathematically, it says that if you take the integral of a constant times a function, you can instead pull that constant out and do the integral of the function inside. Okay, and I basically just expressed in English what's written up here in math. Okay, so as an example of that, I have this function down here. Right, I have 1 over 9x. Okay. And so your goal here is to look at it and see, do you recognize this as a constant times some function that you know how to integrate? So hopefully you recognize this as this is the integral of 1/9 times 1 over x dx. 1/9 is a constant. 1 over x is a function I know how to integrate. I can pull this 1/9 out and get 1/9 the integral of 1 over x dx. And then at this point, I'm back to just one of those basic rules I memorized. This is 1/9 the natural log of the absolute value of x plus c. Right? I can't emphasize enough how integration, the actual process of integrating, like doing this last step, is supposed to be easy. It's this manipulation part that where we figure out how to rewrite it and get it down to the easy part. That's really the skill of integration and the thing that we're working on developing as we go through this unit. At this point, I want to remind you again of our guiding principle. We only know how to integrate 5 basic functions. Anything that's more complicated than that, you absolutely have to do it by accessing special rules. So I've got this example here that's going to put together the addition-subtraction rule and the constant multiple rule. And I'd like to ask you guys to work through this problem and please show all of your work for it. Like, be obnoxious in sort of writing out each step of this thing and doing it carefully. I promise you, if you're willing to do that for a while, you'll get good enough at this that it will feel comfortable and okay to take those things away, and you won't lose your accuracy at that point. So my thinking here is pause the video, make sure you try this on your own. I see here that this is separated by subtraction and addition. So my first step here is going to be to separate this into 6 over x dx minus the integral of 4 cosine x dx plus the integral of e to the x over 7 dx. Okay, so now I split it into 3 smaller integrals, but each of these also has a number in it. And so I need to deal with that part next, right? In the next part, I'm going to write these as the constant times the function that I see. Okay, similarly here, this is clearly 4 times cosine x dx. And this last one is 1/7 times e to the x dx. Now, each one of these things is a constant multiplied by some function that we know how to take the integral of. So my constant multiple rule here tells me, all right, I'm allowed to take that constant 6 and bring it outside. I'm allowed to take this constant 4 and bring it outside the integral. And I'm allowed to take this last constant 1/7 and bring it outside of the integral. And what we have here, and again, I want it to be really plain to you, what I'm left with at the end is 3 really simple applications of rules that we should have memorized. Right? This first one becomes 6 times the natural log of the absolute value of x. The next one is 4 times, let's see here, the antiderivative of cosine is sine x. And the antiderivative of e to the x is e to the x, and we put our plus c. Right? Like, integration in the actual process at the very end is easy. It's the getting there. It's the setting the problem up that sort of takes work. Now, everything I've covered so far in this video has been pretty straightforward, but there's actually quite a few fairly complicated things that we can do with just these basic rules. And so what I'm going to do in the rest of the video is cover some sort of like advanced algebraic manipulation techniques that you can use to deal with problems that just look strange. So again, the rest of this video is all going to be about algebraic manipulation, which as far as I'm concerned is like our only hero when it comes to complicated integrals. Okay, so technique number one, polynomial multiplication. You might encounter an integral where you have two polynomials that are multiplied together. And right now I can't do this integral. You can't just do the integral of these four pieces and then say, yay, I'm done. Like there is no product rule for integration. Okay, if that was a plus in between, sure, no problem, but it's not. Right? So what we need to do here is we need to manipulate the inside of this, manipulate the integrand to make it something that I can take the integral of. Okay, so I'm thinking here I could multiply these polynomials. If I multiply these together, x squared times x is x cubed, x squared times 3 is plus 3x squared, negative 4 times x is minus 4x, and negative 4 times 3 is minus 12. At this point, I've taken this original thing, and I've done a simple algebraic manipulation to get this, which should be really for us to integrate. If you haven't already done this on your own, make sure that you pause the video and try it on your own. So let's see here. I'm going to use the addition and subtraction rules, and I'm going to use the constant multiple rules to sort of break this down into little pieces. This is going to be the integral of x cubed dx, and then it'll be plus 3 times the integral of x squared dx, and then minus 4 times the integral of x dx, and then finally minus the integral of 12 dx. Okay, so this first one, we're going to get 1/4 x to the 4th power. I'm just increasing the power by 1 and multiplying by the reciprocal. Here, again, I'll increase the power by 1 and multiply by the reciprocal. So I have 3 from the outside times 1/3 x cubed. So we can see those 3's are going to cancel out. Yay, good news. Over here, I'm going to have 4 times increase the power by 1, multiply by the reciprocal. And then finally, down here at the end, when we have just a constant, the way that we found the integral of that was just by doing 12x. Okay, and the reasoning for that, by the way, is that we know that the derivative of negative 12x is negative 12, and that's what we wanted. And we remember our plus c at the end. The last thing we'll do is just go through and clean this up. 1/4 x to the 4th plus x cubed minus 2x squared minus 12x plus c. Again, if we had time or if we were interested, we could take the derivative of this function and we should be able to get back to our original function. It would actually take us back to this thing, which we could then factor into this to make sure that we had done the problem right. Another sort of advanced algebraic technique is the idea that you can always split up large rational expressions. Okay, if you have multiple terms in the numerator, terms are separated by subtraction or addition. If you have multiple terms in the numerator and only one term in the denominator, you can basically split this into 3 separate fractions. So I could rewrite this as the integral of 4x to the 7th over x cubed minus 3x cubed e to the x over x cubed minus x over x cubed. And you might be wondering, like, why am I allowed to do that? The reason I'm allowed to do that is that these 3 rational expressions all have a common denominator. I'm basically just undoing the process of combining 3 fractions that have a common denominator. Okay, now that I've separated these, each of these 3 rational expressions can be simplified, right? The first one can be simplified to 4x to the 4th power. The next one, the x cubes are going to completely cancel out, and it'll leave me with 3e to the x. And in the last one, these will cancel out and leave me with x to the negative 2. Right? I now have 3 much, much, much simpler things that I can split into separate integrals. Let's see, and I suppose I could think about that constant multiple rule at the same time. I could pull the 4 out. I can pull out the negative 3. And here, I guess it would just be the negative. Again, I've taken this complicated problem, done an algebraic manipulation to split it apart, simplified the pieces, and then split them into individual integrals using the sum and difference rule, and then pulling the constants out using the constant multiple rule. Okay. The rest of this integral should be really straightforward. This is 4 times 1/5 x to the 5th minus 3e to the x minus, now let's see here, I would increase this power by 1 to negative 1, and then multiply by the reciprocal of that, and then put plus c. So when I go back and pretty this up a little bit, 4/5 x to the 5th minus 3e to the x. Let's see, this is going to become positive, so plus 1 over x plus c. And there it is. The next tactic is a fairly simple one, but it's one that still bears mentioning. Remember that any expressions that are on the bottom of a rational expression can be effectively brought up by using negative exponents. Another thing that I'll mention here also, and it just sort of goes with this specific example, is that it's important to remember when you've got a radical expression like this can be rewritten as a power by remembering that the power that's here goes on the top of this exponent, and the type of root that you have goes on the bottom of this exponent. Okay, so I want you to put those facts together, that information together, to think about what algebraic manipulation you could do to rewrite this, and then try and work out this integral, and then we'll work through it together. So what I'm going to do here is I'm going to rewrite this as 4x to the negative 1/3 power. Right? That power is negative because it was in the denominator, and it's 1/3 because there's only one x there, and it's a cube root a third root. At this point, I can use the constant multiple rule to pull out the 4. And then from here, I use the power rule. I'm going to increase this power by 1. Increasing the power, like, literally just means adding 1 to it, adding 3/3. So this is going to become x to the 2/3 power multiplied by the reciprocal. And then we still have our 4 there and our plus c. Okay. We can finish this out by reducing this down and getting 6x to the 2/3 power plus c. And we're done. The final tactic that I want to talk to you about is this idea of combining radicals with the variables next to them. And I'm really just mentioning this one because from experience, I've seen a lot of students miss this idea, right? We know, hopefully at this point you recognize, I can't just take the integrals of these two things separately from one another. I have to write this in a way that perfectly mirrors one of the original rules, or those original handful of rules that we have. And so know that when you have a radical like this, you can write it as an exponent, and then you can multiply that with this to effectively add the powers together. So I'd like you to pause the video, figure out how you would do a rewrite of this, and then do that integral, and then we'll check it. So what I'm going to do here is I'm going to rewrite this thing as, I'm going to pull the 8 out early, like why not? This is 8 times x squared times x to the 1/2 power. Okay. At this point, I know that I'm allowed to add these exponents together because they have the same base. So this is now 8 times the integral of x to the 5/2 power dx. Right? At this point, it mimics one of the rules that we have. This is just going to be the power rule. Okay, so as we've done multiple times before, I just need to increase this power by 1. That means the power is going to become x to the 7/2. I'm going to multiply by the reciprocal of that because that's how we do the power rule. I still have my 8 and I have my plus c. When I simplify this, I get 16/7 x to the 7/2 plus c. And that's it. That's our answer. So this has effectively been a brief overview of all of our sort of basic integral understanding, and we need to make sure that we're solid on this before we can start to investigate our first advanced integration technique. So best of luck as you work through these things. If you have questions, as always, please let me know so that I can help.